Hooke's law states that the force needed to extend or compress a spring by some distance is proportional to that distance. We determined the spring constants of 3 different springs by adding a mass to each spring and measuring the change in length. The first had the lowest spring constant at 1.94 newtons per meter. The second spring had the medium amount of spring constant at 3.31 newtons per meter. And the last spring had the highest spring constant at 95.1 newtons per meter. We had to add more mass to the last spring because its spring constant was so high. We observed how changes in mass would affect the period of the spring. We used 3 different masses of 20, 50, and 70 grams and measured the changes in time in each period. The average period for 20 grams was 0.527 seconds, 50 grams was 0.806 seconds, and 70 grams measured 0.950 seconds. We concluded that the greater the mass, the longer the period. We determined the spring constants of 3 different springs by adding 50 grams to each and determining the differences in time of each period. The first spring had a constant of 3.45 newtons per meter and resulted in the shortest period of time of 0.811 seconds. The second spring had a constant of 1.90 newtons per meter and an average period time of 1.13 seconds. The third spring had the lowest constant of 1.35 newtons per meter, resulting in the longest period of 1.40 seconds. Therefore, we can conclude that the higher the spring constant, the shorter the period. We observed how a change in amplitude would affect the period by adding 50 grams to the spring with a spring constant of 3.12 newtons per meter and changing its displacement by 3, 6, and 9 centimeters. Then we measured the differences in the periods. The spring displaced 3 centimeters at a period of 0.809 seconds. The spring displaced 6 centimeters at a period of 0.810 seconds, and the spring displaced 9 centimeters at a period of 0.809 seconds. From this, we can conclude that amplitude has no effect on the period.
We experimented with how changes in the length of a pendulum would affect its period. Each had a 50-gram bob and was dropped from an amplitude of 10 degrees. The first pendulum had a length of 20.4 centimeters and had the smallest period time with an average of 0.836 seconds. The second was 31.4 centimeters long and had a period time of 1.07 seconds. Our final pendulum had a length of 66.2 centimeters and had the longest period time of 1.66 seconds. Therefore, we concluded that the longer the pendulum, the longer its period. Next, we determined how changes in the mass of the bob would affect the pendulum's period time. Each pendulum had the same length of 28.6 centimeters, and each was dropped from 10 degrees. The first bob had a mass of 20 grams and an average period time of 1.02 seconds. The second had a mass of 50 grams and a period time of 0.984 seconds. The third bob was 100 grams and had a period of 1.05 seconds. Since these times follow no logical pattern, we concluded the mass of a pendulum's bob doesn't affect its period. We observed how changes in the amplitude from which a pendulum was dropped would affect its period. Each pendulum's bob was 50 grams and each had a length of 28.5 centimeters. We dropped the first pendulum from 5 degrees and it had a period time of 1.03 seconds. The second was dropped from 10 degrees and it had a period of 1.06 seconds. The last pendulum was dropped from its max point of 15 degrees and had a period of 1.05 seconds. These numbers have no correlation, so we concluded that dropping a pendulum from different amplitudes doesn't affect its period time. These first waves are transverse because
the particles vibrate perpendicular to the direction of wave motion. The wave is traveling to the left as the particles vibrate up and down. This wave is longitudinal, meaning that particles vibrate in the same direction as its motion. An example is a sound wave.
this first wave is a pulse wave because
Only a single traveling pulse. Contrastly, this wave is periodic because pulses are continuously generated at one end of the spring.
this wave is one with a free boundary because
Spring is free to move as usual. Because of this, the wave travels back on the same side as it did when approaching the end. This next wave is considered fixed because the spring is held in place at the end. This causes the wave to reflect on the opposite side.
these waves demonstrate constructive interference.
Because both individual displacements occur on the same side. Therefore, when the two waves meet, they will add up to form one resulting wave. These waves show destructive interference because the individual displacements occur on opposite sides. When they meet, the displacement of one pulse is subtracted from the displacement of the other.
We experimented with how changes in the amplitude
Of a wave would affect its velocity. The first wave had an amplitude of 0.228 meters and an average velocity of 4.89 meters per second, calculated by using the equation v equals d divided by t. The second wave had an amplitude of 0.456 meters, and its velocity was 4.96 meters per second. The final wave had an amplitude of 0.684 meters and had an average velocity of 5.61 meters per second. Since there was no significant difference between the velocities of each wave, we concluded that the amplitude has no effect on velocity.
we demonstrated how changes in the tension of the
Spring would affect the velocity of the wave. The spring was first stretched 3.42 meters, and its wave had a velocity of 4.62 meters per second. The second time, the spring was stretched 4.1 meters, and the velocity of its wave was 6.61 meters per second. The third time, we stretched the spring 4.79 meters, and the wave's resulting velocity was 8.71 meters per second. Based on this, we conclude that the greater the tension, the faster the wave.
Next, we experimented with
how the number of standing waves the spring had would affect the velocity of the waves. When there was one standing wave, it had a velocity of 9.71 meters per second. With two standing waves, each had a velocity of 7.28 meters per second. With three standing waves, the velocity was 8.31 meters per second, and with four standing waves, the velocity of each was 9.1 meters per second. Therefore, we conclude that the number of standing waves present doesn't affect the velocities of the waves.